All right, chapter 5, question 136. A 10-liter container is filled with 0.10 moles of H2. I'll write all this up top here. So moles of H2. H2 is 0.10. Container's 10 liters. V equals 10 liters, 10 liters. Where are we here? Heated to 3,000 Kelvin. Wow. Equals 3,000 Kelvin. Causing some of the diatomic hydrogen gas to decompose into monoatomic hydrogen gas. The pressure is found to be 3.0 bar. Right, so that is pressure equals 3.0 bar. Right. Find the partial pressure of the monoatomic hydrogen gas that forms from the diatomic hydrogen at this temperature. Right, that is an interesting question. Okay, so the first thing we can do, we can solve for the total amount of moles that we have at the top, because we have the volume is staying the same. For like final pressure we've been given, and the we have pressure, we have volume, we have temperature. We got everything that we need. R is a constant, so let's just let's find our final moles. So what we're calculating right now is going to be the moles of H2 plus the moles of H. So let's do that. So this is moles of H plus H2. All right, this is going to be equal to PV over RT, our good old friend for RT. Okay, so let's start doing some conversions here. We're given 3.0 bar. We want kilopascals as at 100 kilopascals per bar. So that gives us, well, let's just write this out. We'll just multiply it. All right, per bar, that's going to cancel the bars. Okay, there's pressure, looked after. Next, volume is in liters. Yay. Nothing doing there. Okay, next we get ideal gas constant, 14 joules per mole Kelvin times 3,000 degrees Kelvin. Look at that. Very little conversions. Okay, that works. We get kilopascal liters. That takes out the joules. We are left with moles. Excellent. Everything we want. That gives us a grand total of 0.1203. So there's our final moles there. So we're gonna put that up here. So moles of H plus H2 equals 0.1203. Okay, let's make a little bit of space. All right, so we don't have information to directly determine how much of each went. We can though write an easy expression for this. Like, we know that this here, like your original amount of moles of hydrogen, there's no other hydrogen being introduced, right? So the hydrogen is going to lose some component, right, which is going to split in two, right, to form the moles of monoatomic, right? So it's like minus X plus 2X, so to speak, right? So we can use our expression here to solve for X, right? So we can write 0.10 moles of H2 minus X plus 2X, right? And this should give us the grand total of the moles that we solve for here, 0.1203. Minus X plus X is just going to give X, so X is equal to the difference of these two numbers, 203 minus 0.10. right? Which means that X is equal to 0.203. Okay, so X in this case, remember, this is the amount of moles of diatomic hydrogen gas that are being lost, which means that the amount of monotonic hydrogen we're adding is 2x, right? Cannot forget that. So this means that the moles of hydrogen gas equals 2 times this number, right? 2x equals 0.0406 moles. There we go. Okay, so now we wanted the, I think we wanted the partial pressure of it, right? Partial pressure of the monatomic hydrogen, yeah. Okay, so let's put that figure up there. Moles of Hg equals 0.0406. I'll erase us some room. And we'll solve for that thing with an abbreviated version of Dalton's law of partial pressures. Just like that. So we get 0.0406. Sorry, this is moles. Times 8.314 joules per mole Kelvin. And so moles are gone. That's being multiplied by 3000 Kelvin. So Kelvin is gone. And we're dividing out by 10 liters, right? And joule is equal to a kilopascal liter. So that means that this divided by liters is going to give us just kilopascals. And it gives us a total of 101.3 kilopascals. And there's our partial pressure of monatomic hydrogen.